Hi everyone. Here we are with another another week, and the topic of this week will be conducting daylighting analysis, particularly as it's utilizing, the BIM model, right? This sort of data resource that allows us to correctly geographically position a building within space. It's quite valuable and it really lends to conducting a fairly accurate daylighting analysis. So let's just sort of go over some of the basics and fundamentals of providing a daylighting analysis. Using BIM, some applications, it's called a right to light or solar envelope, which is essentially how a group of buildings may have access to direct daylight. This sort of idea of right to light and solar envelope relates to a lot of actually zoning regulations that require sort of setbacks of buildings, so that light can penetrate through and there's not an overcast of shadows sort of too densely. And so we can utilize daylighting analysis as a way of sort of planning out where a building may exist on a site or a group of buildings and how they may interact with one another for solar access. Which then also using daylighting analysis, it can inform the building massing and orientation of it. We can use analysis to inform the internal organization of rooms in a space. We can evaluate the energy offsets of daylighting versus electrical energy. I mean, if we can determine that, a space can be daylit 70% of the time and hit certain illuminance levels that are acceptable to perform an activity, then we know that reduce electrical demand in these spaces during these times of day. And then I won't say most importantly, but the focus of what we'll be doing is verifying lighting comfort objectives, right? As that will really be the emphasis of what we're interested in, sort of throughout the assignment this week. So some common measurements used in sort of daylighting analysis. There's actually a lot more, but this class it's mostly about BIM and energy analysis and ecology. So this presentation I'm giving right now is just intended to be a very quick overview of daylighting. I mean, there's certainly a lot of college seminars and graduate classes that look at just daylighting. So when I say common measurements, I mean common to what we'll be looking at this week. And the two main ones being what's called the daylight factor, which is the ratio of light available external to a building versus light that's actually making its way inside the building. And this daylight factor measurement is actually really becoming quite popular in sort of the daylighting realm in building science practices. So it's really advancing. And then we have illuminates, which is lumen per surface area, commonly measured in foot candle or lumens. This luminance is, I mean that's like the standard go-to really of how to measure the effectiveness of daylight in a space. So some significant considerations when conducting a daylight analysis is we have the type of analysis that we're performing. What is the measurement that we're trying to understand? Is it a grid plan based? So is it taking a plan, like a floor plan, and dividing it up into a grid? Perhaps another aspect of this grid is what is the density of it? What is the spacing? What is the modules? Or is it three-dimensional? Right? We'll explore both a plan-based method and a three-dimensional method this week. And then there's also the sort of quantitative versus qualitative aspect of not only doing a daylighting analysis, but just in general of being an architect or an engineer or a contractor or what have you. Is there's definitely this sort of prescriptive, this is hitting this illuminance value at this point in time, but what does that really feel like to the human eye and the human experience? Other considerations is time of day that we're conducting the analysis. I mean, different times of days are going to have obviously radically different daylighting results because the sun moves. The architecture and interior design play an important role. There's the sort of form of the building, and then the sort of apertures, locations, whether they're windows, whether they're skylights, whether they're sawtooth configurations. I mean, it's endless. Then, of course, there's the interior design, the sort of placement of furniture, and how that may impede daylighting. The building schedule is an important thing too. What are the hours of operation building is in use, right? Because if we're trying to design sustainably, we want to connect that building schedule to the sort of daylighting opportunity, or design the daylighting opportunities to correspond specifically to a building schedule. There's the building use type. The building use type, extremely important too, also known as the activity type, because this informs what luminance values we are pursuing in our decision-making process, as we're not only conducting an analysis to verify that these values are being met, but also as we may look at design changes and modifications. We want to hit sort of specified values generally. There's the material properties, there's the reflectance of surfaces, so walls. I mean, a white wall is going to have much greater reflectance of light than, let's say, I don't know, a gray or a black, or anything darker really than a white wall will have a much lower reflectance. As one example, I mean, there's the, when I'm saying surfaces, I'm talking about walls, ceilings, floors, work surfaces, desks. I mean, all of these things can really play into the effectiveness of daylight entering a space, because the way we perceive light is the total summation of light entering, then being reflected, then hitting the retinas, and all this. So, but those specifics are really part of other classes. There's the material, in addition to the reflectance of surfaces. Glazing can play a huge role in the amount of daylight that's available, because there's these factors. There's what's called the visual transmittance, which is the percentage of light that's able to pass through a glass panel. There's the it's called the solar heat gain coefficient, so it's essentially the amount of solar energy that can pass through glazing. The number of layers of an assembly have a huge effect, and then the thickness of that assembly. Right? Because if we take, I don't know, maybe a typical curtain wall, we may have, yeah, sure. So curtain wall, we may have like 2 panes of glass that are, I don't know, a quarter of an inch thick, and then, an 1 inch to 1.5 inch air gap, and then another 2 layers. I mean, that can really make a difference of what that thickness is, and what the air gap difference is between those panes of glass, and what each pane of glass is too, because the different panes can have different visual transmittance or solar heat gain coefficient values. I mean, all this stuff factors in, but only if we're doing a kind of analysis that considers these things. So something to keep in mind. And then there's also what's called the plane of analysis, because we can run an analysis, but then we have to determine at what height off the floor that we are considering the analysis, right? So the standard, at least for LEED, for the Illuminating Engineering Society for Interior Spaces, is 34 inches off the floor plane, because that's considered a work surface. But I mean, when we're talking about daylighting, it's really an art and a science, because we're dealing with these sort of very quantitative, numerical results. But if we're intelligent about thinking about how one uses a space, that work plane may really vary. I mean, sure, people sitting around at a cubicle in an office environment, yeah, I buy into that 34 inches. But someone working, I don't know, on an assembly line where perhaps their equipment is elevated, I'm not sure about the 34 inches. Or perhaps they're even working even lower. I mean, what do we think about, like, let's say a child's classroom, sort of maybe a K through 5 classroom. I mean, their desks are significantly smaller and sit lower to the ground, but we still want them to have that sort of benefit of daylighting. So a plane of analysis just needs to be considered, and realizing that it could vary based upon the type of building and use of a space. So one type of analysis that we are going to do is LEED verification. I assume everyone's familiar with LEED. It has its pros, it has its cons. At the end of the day, though, it does provide a sort of system for measuring the green performance or sustainable performance of a building. So we can use our BIM models to do design benchmarking, saying, is the design meeting LEED objectives? The downside to LEED verification is it primarily factors in building geometry and aperture. It's because it just really creates a relationship between the amount of open space, normally in plan, and then how that relates to a ratio of the floor area. And so it doesn't really account for material properties of glazing, which, as I just said, could have a pretty profound effect on the efficiency of daylighting, because visual transmittance determines how much light can actually pass through glazing. But that's neither here nor there. It is what it is. Daylight autonomy is another metrics or type of analysis that's really becoming more popular. It's becoming one of my favorites, maybe. It's because it matters. It measures the percentage of hours spaces will achieve being lighted by natural daylighting throughout the entire year, and then it's also climate based. So I think this is more realistic rather than the LEED, because it takes into the specifics of the climate conditions. It takes into the specifics of materials at times, but then the daylight autonomy, and we're not going to get too much into it in this assignment, because I do need to sort of limit the amount I ask from you. But daylight autonomy in your Revit model is it can look at both electrical lighting and daylighting and provide sort of ratio differences. But we'll just be using daylight autonomy to say, hey, what is the percentage of time spaces are being naturally daylit throughout the year? It's incredibly useful. And then we've got illuminance analysis. Most illuminance analysis are done through the using these sort of sky files, sky conditions that are all standardized. They're determined by the International Commission of Illumination Standards. Their most common illuminance analysis are most commonly used for determining lighting comfort conditions. Again, hitting these benchmarks, these sort of this is what the space should be to support activities. Often in luminance analysis is used using the grid-based method. That can also be three-dimensional. Often achieved using grade-based is three-dimensional method. That's sort of really bad wording of that. But yeah, so let me often using grid-based or three-dimensional method. So there we go. What else? The luminance analysis does often account for material properties of materials. So often account for material properties of construction materials or assemblies. Would be a better way to put that. As a result, I prefer luminance analysis over the lead because I like reality. But all these different types of analysis have different usefulness based upon the design process is always corresponded to time available, right? So some design and BIM modeling objectives as we're thinking about daylighting. We want to meet lighting targets and thresholds. We want to reduce energy demand by allowing more daylight to enter our space. We don't want to over or underlight a space with natural daylighting. There is such a thing as providing too much light because it can be blinding, right? If we just have like sort of way too much light, it can be blinding. It can sort of create solar hotspots. I don't know if anyone's encountered this. One of the earlier architectural offices I worked for actually had this great skylight in our sort of studio. And there's this table that this skylight sat above, and it was sort of like the official plan review table. But, oh man, for whatever reason, the type of glazing that was used, despite really nicely lighting the space with natural daylight, it just fried the area because there's too much sort of solar penetration, too much solar radiation penetration. So it's in consideration when we're thinking about daylighting. And then there's also when too much daylight's being introduced to a space, or eyes can only see so much. And then there's also the concerns of glare and too great of contrast, because as things become more and more contrasted, the harder we have an ability to see them clearly, because it strains our eyes essentially. So if we have maybe a sort of center of a room, like with this skylight I'm talking about, providing all this natural daylight, but then the walls are dark, it creates a very uncomfortable condition. So generally we want what's also called uniform lighting within zones of a building. That's why, as well as a number of buildings that are naturally daylit will also see supplementary electrical lighting. That's normally there to sort of create more of an equal balance throughout a space. But another thing to consider is when we're providing natural daylighting, we want to provide it, but we don't want to completely diminish the thermal efficiency of a building envelope. Every time we create a window or an opening, we are creating a glazed area within the building shell, which I can almost guarantee is almost always less thermally efficient than something like, I don't know, a metal stud wall with insulation, or a brick wall, or even a concrete wall. I mean, you practically know, like, glazing is the least thermally efficient building assembly most of the time. Now it depends upon where one is residing. In areas that we may want a lot of solar radiation entering the interior space for passive heating purposes, that may be different. But as we sort of evolve in these analyses that we're doing and design recommendations we may have, we need to begin thinking about the integrated impact, right, of these things. And so this is one of them, is that, yes, okay, great, we can provide more natural daylighting, but what does this do on the thermal energy side? So something to think about. Some additional opportunities for analysis that we're not really going to get into, but can be done quite easily with a BIM model, using scripts, using alternate plugins that we're not necessarily using. I mean, there's a Dynamo script to do views to the outdoors or to do a glare analysis. I mean, both these are beneficial to look into, just sort of depending upon the condition, particularly the views to the outdoors, because if one's pursuing LEED or, just wants to be good with their building design, you can start to look at what is the opportunity to create a nice view to the outdoors while also creating the necessary amount of natural daylighting without totally, reducing the amount of thermal efficient envelope. So, okay, so that's a really quick crash course overview of the sort of basics of daylighting. Like I said, this isn't necessarily a daylighting course, so I'm not getting into all the nitty-gritty detail. I'm just trying to be really focused on what are the analyses we can perform using a BIM model, what does the analysis provide to us, and what are their maybe direct applications. So with that said, now I'm going to go over some process steps of going through the analysis in the following videos.